This is Radio Eco Shock with Alex Smith.
Welcome back to a new season of Radio Eco Shock. I'm Alex Smith. We have two top climate scientists standing by for our interviews, Kevin Trenberth and Dennis Hartman. But first,
2 months of weather madness in 10 minutes.
billions of people just went through extremes of heat, drought, floods, and even polar cold. This is new, something completely different for humans and all living things. We lack the language and images to comprehend this blast from the hotter future. As we go on the air, about 1/3 of Pakistan is underwater. Floods have killed over 1,000 people and displaced millions, wiping out homes and possessions of already poor people. The floods followed relentless roasting heat, starting early and staying long. The Pakistani government is clear. This battering by the elements is caused by climate change, and the people of Pakistan are not to blame for that. Industrialized countries built on free discharge of carbon into the atmosphere caused this and should pay restoration costs. Here is a clip from Pakistan's Minister for Climate.
We are at the moment at the ground zero of the front line of extreme weather events in an unrelenting cascade of heat waves, forest fires, flash floods, multiple glacial lake outbursts, flood events, and now the monster monsoon of the decade is wreaking non-stop havoc throughout the country.
Of course, the guilty parties will not pay, despite years of pledging billions for a climate fund. A few charities and aid aside, the poorest victims of climate change are being left on their own. Let's talk about the scale of the disaster in Pakistan, besides the country being 1/3 underwater. These are the developing numbers as told by tweeters Bina Shah and Eric Fagelding. 1,350 people killed. I think that's a real underestimate, and we'll see what happens as starvation comes in. 50 million people displaced. 50 million people out of their homes, out of their communities, out of resources. 900,000 livestock deaths. So that's about 80% of all the cows and sheep and goats that were in the country. 1 million houses washed away. 40 reservoirs, at least 40 reservoirs breached. 220 bridges collapsed. 90% of the crops were damaged. They estimate 10 billion lost to the economy. I think that's a tiny underestimate. So we don't know. This is a very complex country. Reports are still coming in. We'll see how big this is, but it's historic, and I don't see the world responding at the speed that is needed. There should be planes loaded with aid just crowding into the airport, ships with aid steaming towards their food, all the things that will be needed for these people.
Ladies and gentlemen, I'll give you every detail as long as I can talk and as long as I can see.
The other untold headline story is the new summer in China. Across this large country, heat arrived early, broke record after record, and stayed not just days, but weeks and months. The major producing region of Sichuan had to shut down factories for name-brand companies like Apple and Intel because of heat and lack of electricity. Rivers and lakes ran so low they exposed relics from the Middle Ages, and of course hydropower was slashed. Crops and landscapes were baked dry, wildlife disappeared, some burned out of their habitats. The heat wave lasted 8 weeks. Not only were daytime high records broken day after day, but nighttime temperatures stayed above 30 degrees C, 86 degrees Fahrenheit. People could not cool down at night, and that is very dangerous for health and for fatalities. Korea suffered through long-lasting heat waves too. Heat in China went over 40 degrees C in many provinces, hitting 44.6 C or 112 Fahrenheit in Sichuan, Hubei province. Some temperatures are underestimates because the Chinese government has a habit of capping public weather reports at 40 degrees C, even when car and home thermometers posted on the net went closer to 50 degrees C, over 120 degrees Fahrenheit. Now, the government of China is among the most aware of climate risk. Every year, China installs more alternative energy, like solar, than the whole rest of the world. The government provides more funding for Chinese climate science than most others, including the United States. But now the Chinese people, too, know that rapid action is needed. Nobody wants to live through that heat every summer. We do not know how much of China's crops survived. In Japan, over 1,000 all-time heat records were broken in the summer of 2022. Tokyo sweltered for weeks. Productivity was down. Japanese of all ages suffered. And like people everywhere, they began to fear the future in a destabilized climate. I have an interview in a coming show about the hit to well-being as climate change ramps up, the mental impacts. Most of this heat news from the Far East was barely reported in Western media. Europe and North America had their own heat problems. No doubt you heard about the unbearable weeks of heat in Spain, along with wildfires torching whole landscapes. That spread into France this summer, setting more records. Wow, what happened in France this summer? Rivers in France and Germany went as low as they did in China, again revealing rocks and ships not seen for hundreds of years. Electricity generation in France plummeted with low rivers. Some of them looked like sandbanks, and essential German barges had difficulty finding enough water to navigate the Rhine River. When rivers die or dwindle to puddles and narrow creeks, all kinds of wild things die, from insects to plants and mammals and amphibians. River regions are ecological hotspots. We barely know the fisheries and all the things that died off in the long 2022 heat waves and drought.
Global heat.
When this program began in 2006, heat covering a whole continent was remarkable. A few years later, I reported on the first transcontinental heat, stretching from North America right over to Northern Europe. But this is the very first summer I have seen a global hemispheric heat, sweltering through long-lasting weeks. You know about the horrible heat in the southern United States, wafting up from time to time into the eastern seaboard. The U.S. Southwest went through its 14th year of drought, with more massive wildfires, especially in California. Even in the first week of September, 11 states in the American West went over 100 degrees Fahrenheit or 37 degrees C. Again, weather reporting from North Africa and the Middle East seldom filter through Western media and to our minds. Heat maps of North Africa this summer made me cringe. They went over 50 degrees C, 122 Fahrenheit, regularly, on and on. Is it any wonder that countless millions of people in North and East Africa are out of food, starving? Their emissions did not bring this new climate. We did. North Africa is becoming uninhabitable for months every year. In Touradon, Morocco, 4 a.m., the temperature was still 40.4 degrees C, 104 Fahrenheit, and that was supposed to be the coolest time of the night, just before dawn. Hot winds were blowing. Oh, Iraq and Iran. Few of my listeners could live through those extreme temperatures in the Middle East this year, especially without air conditioning, as hundreds of millions of people did. In early August, the highest temperature in the world was in Abadan, Iran, 53.0 degrees C, 127 Fahrenheit, in the shade. In Iraq, Basra held the world's hottest August 2022 day with 52.6 degrees C. That is a city of 1.3 million people, most without air conditioning. The electricity is not reliable. It's spotty, even to run a fan. In the Gulf state of Qatar, the hottest August day ever recorded was on the 8th with 49 degrees C, 120 Fahrenheit. 2022 is a summer to remember. The first all-out record-breaking global heat wave struck the northern hemisphere. Then, when it broke down, it was flash floods in many countries. The heaviest rain ever measured in Korea's capital of Seoul struck on August 8th. It was crazy, with homes, roads, everything under feet of water in a couple of hours. Similar flash floods washed out cities in China and in the United States, from Kentucky to Nevada. The hotter air carries more moisture, so when it does come down, it's the deluge. King Heat says, "Après moi, le déluge." A lot of this extreme weather is the raw result of too many greenhouse gases in the atmosphere. But the expression of how destabilization happens is channeled by long-standing natural variations in the atmosphere, but especially in the sea. In this program, Dr. Kevin Trenberth will explain the impacts of the La Nina currently at play. Trenberth published his first paper on El Niño, La Nina, in the 1970s, and he remains the authority. Then another world-leading scientist, Dr. Dennis Hartmann, takes us into why La Nina patterns are coming more often, and they are. Improbably, the trail leads back to Antarctica and the ozone hole. We are about to explore the workings of a strange planet, the third in space from Sun.
This is a climate emergency. Find out more on the blog ecoshock.org. No sign up, just the latest info, free for all. ecoshock.org.
We pick up our conversation with well-known scientist Dr. Kevin Trenberth, distinguished scholar at the National Center for Atmospheric Research and author of the new climate guide, The Changing Flow of Energy Through the Climate System. Let's dive into the big system in the Pacific Ocean that drives so much of the weather we've been seeing in the Americas, Europe, and beyond. TV weathercasters point to La Nina or El Nino, but scientists call it ENSO, and that includes another pattern change, the SO part, the Southern Oscillation. Kevin, what is the Southern Oscillation, and why is it grouped with La Nina and El Nino?
Yes, so the ENSO phenomenon, the El Nino and Southern Oscillation phenomenon, is the largest form of natural variability that occurs on the planet. It involves the entire Pacific Ocean, and that's the El Nino part. El Nino refers to a warming of the central and eastern Pacific, east of the date line, but all the way across to South America. And as a result, it's, over a quarter of the tropics, the planet. It's a much larger area than the United States, for instance, that is warming with an El Nino event. And the other phase is a La Nina event, which is a cold phase of the phenomenon. Now, the best way to think of this is that what goes on in the ocean is the El Nino and La Nina. And in the atmosphere, the corresponding phenomena is primarily this thing called the Southern Oscillation, which was first discovered by Sir Gilbert Walker when he was trying to figure out what was going on in India around the early 1900s for the most part. And he was the one that gave it this name, the Southern Oscillation. It was southern, of course, relative to Europe, but it's certainly centered in the tropics, although the Southern Hemisphere probably plays a stronger role than the Northern Hemisphere. And the reason is, in the Northern Hemisphere, there is the very large annual cycle associated with the heating up of land in the summertime and then cooling off with snows and cold in the wintertime. Whereas in the Southern Hemisphere, it's dominated much more by the ocean, and there can be more continuity, more continuous variations in the weather and climate system, the coupling between the atmosphere and the ocean, and it has its primary ability to remember what has happened from one year to the next in the Southern Hemisphere. But this certainly extends to the tropical Pacific, and the biggest changes occur in the tropical Pacific in association with monsoons and the phenomena that we call the convergence zones, the tropical convergence zone and the South Pacific convergence zone. These are the main rain bands over the ocean that move around with the El Nino phenomenon.
And there is an oscillation in the North Atlantic Ocean, and you cover that in your book. It impacts weather in the U.S., the Canadian Northeast, but especially Europe and Scandinavia. What should our listeners know about the North Atlantic Oscillation?
Well, the North Atlantic Oscillation also has a long history, and it was discovered at least 100 years ago. And it relates primarily to changes in the North Atlantic and over Europe and over the eastern parts of the United States. And during one phase, there are very strong westerlies and a southward displaced storm track that takes more warm, moist air into Europe and extends across even into parts of Asia. Whereas in the other phase, the storm track is further north, and so the main storms go into Europe in Scandinavia and affect Russia and so on. And at that phase, the Mediterranean and in Spain and Portugal and so on are very dry and may have heat waves and wildfires such as we've seen in recent times. That's one other phase of the North Atlantic Oscillation. It's unique to the Northern Hemisphere, this particular phenomenon, and it relates very much to the presence and the configuration of the continents, but Greenland plays a key role as well, and it relates to the disruption of any flows that would otherwise go from west to east, as it does more in the Southern Hemisphere, for instance. And so this is what we call a natural mode of variability, primarily in the atmosphere. It doesn't require an ocean component to exist, but the ocean does help it provide a little bit of memory.
But we should know that is a natural phenomenon that's been observed for a long time, and it's not a result of global warming per se.
It's not, but some of the impacts are being affected by global warming, because what global warming does is when it's wet, it tends to be a bit wetter, and when it's dry, it tends to be a bit drier, and the heat waves are stronger and the wildfires are stronger. And so the natural variability sort of sets the stage, but the global warming aspect makes the things that are going on that stage a little bit exaggerated over what they would have been.
But you conclude that ENSO changes in the Pacific are much stronger drivers of global weather than the North Atlantic Oscillation?
Yes, the ENSO phenomenon is the primary mode which we refer to as being coupled. That very much involves both the atmosphere and the ocean. And so as the easterlies, the trade wind easterlies in the tropical Pacific drive the ocean currents in the Pacific, it tends to build up more water over north of Australia and in the Indonesian region, and the warm water tends to accumulate there, as it's been doing now for the last couple of years. And eventually, sea level gets higher. It gets more than a foot higher than it normally is over in that region. It tends to exaggerate some of the typhoons that occur in that region. And then eventually the system says, oh, I can't stand this anymore. And a lot of this water then flops across the Pacific, and we have an El Nino event, and it warms up in the central and eastern Pacific. The ocean is very much involved in this, and as the warm water moves eastward, a lot of the weather systems do as well, and we get a lot more activity in the central and eastern Pacific, and also, incidentally, a bit less in the Atlantic. And so that's what happens in an El Nino event. And the other phase, the La Nina phase, where it's cold in the eastern Pacific, there tends to be more hurricane activity in the Atlantic. And so it has consequences not just for the Pacific and the Pacific Rim countries, but also in the Indian Ocean and in the Atlantic as well.
We have so much to learn. Unlike the way most people in the media talk, you say there is no neutral state in the El Nino-La Nina cycle, and La Nina should really be plural. Could you talk to us about those things?
Well, yes, and so the average conditions in the tropical Pacific are very seldom observed. Instead, it's more like a teeter-totter, a seesaw, where we're going from El Nino to La Nina and then back again. And it's very much related to the conditions that get set up in the tropical Pacific between the winds and the sea temperatures and the changes in the ocean and sea level as a result. And if you're in one phase, then it's causing changes in the ocean that eventually cause it to flip back into the other phase, although the La Nina events can last longer, and we're about to go into year 3, which is very unusual of a La Nina event, whereas the El Nino events can be more intense and have bigger consequences, and the warmest years on record tend to be in the latter phase of the El Nino events. And so the last biggest El Nino event was 2015, 2016, and the warmest year globally was 2016 still, although 2021 was not very far behind, I have to say.
Talk to us about the relationships now between ENSO and climate change. We have this natural pattern probably going on for thousands of years, as we know, with ENSO. But now humans are rearranging everything with this energy flow that we talked about in our first interview. What drives what? How can we separate the two, or should we separate them?
Well, certainly a key question for scientists is how will El Nino change, or how will ENSO change as the climate changes? And it's not that clear, but it's maybe a little bit like a lot of the weather systems as well. The natural variability, it's best to think of this as going along much as it always has. So El Nino will continue in terms of what's going on in the Pacific with regard to the interactions between the atmosphere and the ocean. But what global warming and climate change does is it changes the consequences. So the El Nino phenomenon is the biggest causes of where floods and where droughts occur around the world. And what happens when there are floods and droughts are now worse because of the global warming aspect. And that's because the warmer atmosphere holds more water vapor, and in places where it's dry, usually on land that's favored more in El Nino years, in particular in places like Australia. Australia tends to be very dry and hot, and wildfires in Australia. The last modest El Nino event was 2019. 2020 was when the last huge number of wildfires occurred in that region, whereas the La Nina stage often has more rain on land, at least in the winter half year. But the La Nina phase also tends to push the storm tracks across North America a bit farther to the north, and so it tends to be drier and a bit warmer across the United States in La Nina events, and that's what we've seen in the last couple of years. And it's exacerbated the drought, especially in the Southwest. It's when you have El Nino events that we're more likely to get a storm track that brings major rainfall events into the West Coast and especially into California. But there's always exceptions. There was a little rainfall event in Death Valley just recently, for instance. But more generally, El Ninos favor wetter conditions in California and farther to the east, all the way across to Florida, for that matter.
Do you think global warming will build in more chances of these superheating El Nino patterns?
That's a good question, and there's been some speculation about that. Our climate models, are not quite as good as I would like to see in order to have real confidence in dealing with that particular question. And so I don't think we can answer that very well, but I think when we have an El Nino, the consequences are likely to be greater. And the next El Nino, which is, you can see the signs of it building up in the far western Pacific. The warm pool that normally exists around Indonesia and in that region has built up, and there is very warm water down to 200 meters or below 200 meters in the ocean, sort of waiting for the right conditions for the next El Nino to develop. But, it takes a while to unfold. It takes several months to unfold, and we can actually track that now, and predictions of El Nino are pretty good for at least 6 months in advance. And the predictions for the coming winter are that we will be primarily in La Nina conditions. But beyond that, I think the odds are probably going to favor an El Nino beginning, say, March, April next year or something like that.
Just another small thing I noticed in your book, which could be big. You say ENSO and climate change team up to increase salty ocean deserts. And nobody's talking about this. Is ocean desertification an issue worth watching?
Well, yes. I was one of with some collaborators that analyzed what's happening to salinity, and we have measurements, much better measurements, since about, the early 2000s. There's a lot of instruments in the oceans that are measuring salinity for the top 2,000 meters of the ocean, and we've been able to understand a lot better what is happening with the saltiness in the ocean. And what we've found is that indeed the salty areas are getting saltier and the fresher areas are getting fresher. And so this relates to the general concept that the wet areas are getting wetter and the dry areas are getting drier. So it relates to this particular important role of water vapor and precipitation in climate change. And to some extent this is happening on land, but over land it gets complicated by the availability of water. In deserts there's no water to play a role. But over the oceans, that signature is very clear. And so the salty areas are getting saltier. And when it's salty, that means the water is a bit denser. And so that water is more inclined to sink. And so it has an impact on ocean currents. And it can begin to affect things like the Gulf Stream, for instance. And there's a lot of speculation and worry about what might happen to the Gulf Stream as a consequence of these kinds of changes that are coming about in part because of climate change.
So we saw this summer of 2022 in the Northern Hemisphere, there were long-lasting, record-breaking heat waves along with drought and very extreme rainfall events, as we've talked about. And all this comes during a third year of La Nina. Will we not discover a whole new level of pain when a strong El Nino arrives again now that we've warmed Earth?
There's a number of people, and I think I would include myself in that speculate that this may well be the case. When the next El Nino occurs, the odds are high that we will break the record and indeed establish the next year that we have the highest global mean surface temperature around the world, sort of in the trailing phases of the next big El Nino event. But as a consequence, it means that heat is coming out of the ocean in an El Nino event. It pumps up all of the convection, all of the thunderstorms that occur, all of the hurricanes and typhoons around the world get pumped up by this. And during that, the rain that comes out of those, it warms up the atmosphere as the latent heat is released, and that contributes to this increase in the global temperatures in the atmosphere. And eventually, the atmosphere moves that heat around. It affects just about every part of the planet, but that heat some of that heat eventually gets radiated back to space. And so this is a part of the process of this overall flow of energy through the climate system that an El Nino is actually a means of cooling off the tropical Pacific Ocean, pumping the heat into the atmosphere, and the atmosphere moves it around and then moves it out to space. As it's doing that, of course, it's changing the weather systems, and some of these weather systems can be more extreme than anything we've ever seen before.
Your work helped define the ENSO system in many highly cited papers. What do you find most striking about it?
Well, that's a loaded question, and you can look at it from a physical standpoint, and the understanding has been increased. I was involved in a program that was called TOGA, the Tropical Oceans Global Atmosphere Program, where we first put moored buoys in the tropical Pacific to measure what was going on below the surface. And it was only then that we fully began to understand just what was happening in the Pacific and how it was happening. And that understanding has grown, and it's grown a lot more as we've had more satellite observations from space, especially of precipitation, rainfall, and also of sea level using altimeters in space. And we have tried to replicate that in various climate models. I think there is a broad understanding of why El Nino occurs, and I've tried to describe that a little bit here. But the ability to model all of the details is not there yet, and it relates to the complexity of things like typhoons and hurricanes and thunderstorms that are occurring on quite small scales, and yet we have to deal with global scales as well. And so computers have gotten bigger and faster and better, but they're still not quite bigger and better and fast enough yet to fully do all we need to do with regard to the El Nino phenomenon. And so there's some uncertainties there that still exist, and it's very important to keep this monitoring system in place. All of these moored arrays that have been led by the U.S., but contributed to by a number of other nations, the Japanese in particular, and also all of these floats that occur in the ocean, the so-called Argo floats, that are contributed to by about 49 different nations around the world, including New Zealand, where I am now. And New Zealand also plays a key role in helping to deploy these floats in different parts of the South Pacific, for instance. And so it's very much a collaborative activity. And one of the things which I have been quite involved in is trying to make sure that the importance of all of these observations is fully realized by the funders and the politicians, the agencies and so on, because tracking what is going on is what enables us to make more reliable forecasts 6 months ahead of time. And they probably still have scope to get a little bit better, but there are some unpredictable aspects that will limit how far we can go with El Nino forecasts. Probably ultimately 18 months is about as far as we can go in details because of the chaotic nature of weather.
From Auckland, we have been talking with Dr. Kevin Trenberth, distinguished scholar and a leader in world climate reports. Check out his new book, The Changing Flow of Energy Through the Climate System. You can find out more on my blog at ecoshock.org.
You're listening to EcoShock Radio for the world.
I'm Alex Smith. Get it all at our website, ecoshock.org.
This is Radio EcoShock with your host, Alex Smith.
Strange droughts, flash floods, weird weather. Welcome to La Nina in the age of climate change. Why are La Nina years coming more often? Dr. Dennis Hartman has a surprising answer. It could be the ozone hole. Worse, this trend might hide real warming to come. Published in the Proceedings of the National Academy, August 22, 2022, Hartman's new paper is The Antarctic Ozone Hole and the Pattern Effect on Climate Sensitivity. At the University of Washington, Dennis L. Hartman is professor in the Department of Atmospheric Sciences and senior fellow at the Joint Institute for the Study of the Atmosphere and the Ocean. With about 200 articles published and a long list of top awards, Hartman was a coordinating lead author for the fifth assessment of the Intergovernmental Panel on Climate Change. He is author of the college textbook Global Physical Climatology, now in the second edition. From Seattle, Dennis Hartman, welcome to Radio EcoShock.
Hello, Alex. Good to be with you.
Have there been more La Nina events in the last 40 years than in the longer past?
There has been a trend toward cooler temperatures in the eastern equatorial Pacific near South America that's persisted since about 1980 or so. And that's normally the signature of sea surface temperature anomalies that we associate with La Nina.
And what do more La Ninas mean for world weather?
Generally speaking, the distribution of SST, or sea surface temperature, in the tropics influences the precipitation in the tropical areas, and also there's a pattern that propagates downstream and toward the higher latitudes that influences weather in the extratropics. Particularly in the United States, the La Nina is associated with drought in the southwestern United States, California, etc. So it's generally believed, and the data show, that La Nina events are associated with drier conditions in California, where we're already short of water. And there's also a similar signal that heads out toward the southern hemisphere and influences the weather in the South Pacific and South America.
There's a startling map in your paper that was new to me and probably to our listeners as well. Figure 1 shows a world getting hotter on land and sea, as we might expect, except for two large ocean zones where sea surface temperatures are actually getting cooler. That defies climate models, and it stands out as weird in a heating world. Dennis, where are those strange pools?
The primary ones are in the Pacific. In the South Pacific, just west of the southern tip of South America, over the Southern Ocean, it's been cooling. And also in the eastern tropical Pacific, it's been cooling during a period when the rest of the Earth had been warming rather rapidly.
And what made you think the cold waters rising around Antarctica are related to those cool waters you describe in the tropical Pacific off the coast of Peru and Central America?
Well, there's quite a large literature of climate modeling that shows a physical relationship between cooling over the Southern Ocean, which is what I'm going to call the South Pacific, and cooling near the equator. Not all models do that, but the models that do that have a fairly complex mechanism for connecting those two regions. The cold sea surface temperatures over the Southern Ocean influence the atmospheric circulation, and also cool water travels up the west coast of South America. There's something called the Peru Current, which flows from the Southern Ocean toward the equator. So that carries cool water poleward. And also colder water over the oceans, particularly in the tropics, generally is associated with higher amounts of low clouds. And low clouds shield the surface from solar radiation, and that adds an additional cooling. So in the models that produce this connection between Southern Ocean cooling and equatorial cooling in the Eastern Pacific, this role of clouds in helping the cooling progress toward the equator seems to be very important.
Well, let's get to the ozone hole connection. The public and the media have pretty well stopped talking about the ozone hole over Antarctica. Problem solved since the Montreal Protocol. What is the reality, and how long will the ozone hole remain?
So it takes a very long time to move the chlorine, so-called CFCs, chlorofluorocarbons, out of the stratosphere. The only thing that really destroys them is high-energy radiation that they get from the sun, which breaks these molecules apart, and they only see that high-energy radiation when they get up into the stratosphere. So these chemicals have to be circulated through the stratosphere, broken apart by solar radiation, and then flushed out of the system. And because that process is slow, it's going to take about another 50 years or so before the chlorine levels in the atmosphere return to the levels that they were in 1980 when we first noticed the ozone hole over Antarctica.
At first, I found connecting the ozone hole to Pacific cooling thousands of miles away surprising, but then I found a series of papers, mainly led by Chinese scientists, finding connections between a thin ozone layer over Antarctica and the cycle of El Niño, La Niña, known as ENSO. Could you take some time to explain how a thinning ozone layer could affect waters in the tropical Pacific?
Well, there's a couple different possible mechanisms. One could be through the stratosphere directly, and then somehow that would affect by cooling the upper troposphere in the tropics, that could affect the way convection operates, and that could shift the winds in the tropics, but that's not the mechanism I'm referring to in my paper. Another thing that has been observed about the ozone hole in other papers and in models is that the ozone hole, well, there's a strong circulation in the stratosphere in the wintertime because it's very cold over the pole and warmer in lower latitudes. And that cold vortex also influences the surface winds. When the stratospheric vortex breaks down in the spring, those westerlies disappear. But the absence of ozone due to the ozone hole means that that vortex over the South Pole persists longer into the spring season. And that means that the westerly winds around Antarctica at about 60 degrees south, they actually are strengthened by the ozone hole. So there's fairly strong proof that the ozone hole causes an increase in the surface winds around Antarctica, which are also already very strong, but they get intensified because of the ozone hole, particularly in the spring season. And this results in a cooling of the Southern Ocean. And so my particular mechanism suggests that the springtime winds strengthening associated with the ozone hole causes a cooling of the Southern Ocean, particularly in the South Pacific, and that by the mechanism I described previously, this influences the tropical sea surface temperatures and gives you a little bit of more of a tendency toward a La Nina state with colder temperatures in the eastern Pacific.
Yeah, those winds are pretty well known to yachters and sailors who try to go down towards Antarctica. They're just so strong that people try and avoid that because their life is in danger. Huge waves and very strong winds. Your research also suggests this link between the ozone hole and more La Nina years could hide some of the true impacts of our warming by greenhouse gases. You've hinted at the cause of that. Could you tell us more?
Yes, there's also a substantial scientific literature indicating that this La Nina trend that we've seen in the past 40 years or so has masked part of the warming that we would expect to see from greenhouse gases. And the mechanism whereby that works is one that I've already described. You cool the sea surface temperatures, you produce more low clouds over those lower sea surface temperatures, and that reflects solar radiation. And that increased reflection of solar radiation associated with the trend toward a more La Nina state in the Pacific Ocean has caused a little bit more solar radiation to be reflected, and that's caused the planet as a whole to warm up more slowly than it would have done if we did not have this La Nina trend in tropical sea surface temperatures. It was very interesting because it caused an apparent discrepancy between what the models predicted about global warming and what was actually observed. So understanding the so-called pattern effect on global warming, where the distribution of sea surface temperature can cause an enhanced reflection of solar radiation, which slows down the warming. So understanding that has improved the agreement between what models are predicting and what the Earth is actually doing. So in the absence of that pattern effect, the climate would have warmed up even more quickly than it has.
Would you call increased cloud cover from La Nina, like cool seas, a negative climate feedback?
If you got to be careful about the language. If the La Nina effect is caused by greenhouse gases, then it would be a negative feedback. If, on the other hand, La Nina thing is natural variability or associated with the ozone hole, it's not exactly directly connected with the greenhouse gas forming. On the other hand, there are also theories that suggest that global warming would cause an enhanced SST gradient across the Pacific, at least temporarily. And the mechanism for that is that there is currently a cooler sea surface temperatures in the East Pacific than the West Pacific. And that's caused principally by upwelling of cold waters in the Eastern Pacific near South America. That's where good fisheries are. That's kind of how we got the name La Nina, because it would arrive about Christmas time in South America, and the warm water would come over and shut down the fishery. So that upwelling of cold water climatologically has always been there. But the idea is that when the climate warms up, it takes much longer for the ocean to warm up because it has huge heat capacity. So this cool water would keep coming up in the Eastern Pacific while the rest of the ocean warmed up due to greenhouse gases. And therefore there's a theory for a mechanism whereby the sea surface temperature gradient across the Pacific could increase as a result of global warming. And then that would be a negative feedback, slowing down the rate of warming. But that would be probably only a temporary impact because once the deep ocean warms up, that effect would go away.
Okay, how about this? Can we say a link between the polar ozone hole and tropical sea temperatures is a teleconnection?
Definitely, yes. You have some sort of wind change over the Southern Ocean that results in a wind change and a sea surface temperature change at the equator.
But which is driving which? Are changes around Antarctica driving ENSO-like conditions into more La Nina events, or is it the other way around? More La Nina years are cooling surface waters in the polar Southern Ocean. How does your paper sort that out?
Yes, it could be either, as you're suggesting. La Nina events would cool the Southern Ocean. The way that I handled that in the paper was to take the observations and remove the effect of La Nina from the sea surface temperature patterns. And then once that is removed, I searched for the signal associated with the strong winds over the Southern Ocean. And that showed a pattern that had cooling over the Southern Ocean and cooling over the Eastern Equatorial Pacific. So my argument then was that there is an independent teleconnection from the Southern Ocean back to the tropics, which is also strong. And that's also consistent with a significant amount of climate modeling work and analysis that's been done in the past.
Radio EcoShock.
You are listening to Professor Dennis Hartman on Radio EcoShock. I'm Alex Smith. We're talking about the strange connection between the ozone hole high above the Antarctic and cooling waters in the faraway tropical Eastern Pacific near Peru and Central America. Assuming humans do not emit more gases like CFC, refrigerants, scientists expect the ozone hole should heal in about 50 years. Dr. Hartman, would that break the La Nina and cloud-forming process you propose? And if so, what happens to global warming, say, in the 2070s and beyond?
So if the mechanism I'm proposing has an important influence on the tropical SSTs, and we know that that has an effect on the warming rate, we would expect the warming rate to increase after the ozone hole goes away. But there are other mechanisms that people have talked about which can cool the Southern Ocean. One particular that scientists have become interested in recently is that as the ice in the ice shelves and on the Antarctic continent melts due to global warming, that puts fresh water into the Southern Ocean. And there's a mechanism whereby that can also cool the Southern Ocean. The mechanism I'm talking about is just one of many possible ways in which the changes in the Southern Ocean around Antarctica can influence the climate globally.
Just to remind listeners, SSTs stands for sea surface temperatures. Maybe, though, the ozone hole will not even shrink in 50 years. A new paper published by Rachel Pannett is titled Australian Wildfires Cause the Largest Stratospheric Warming Since Pinatubo and Extends the Lifetime of the Antarctic Ozone Hole. It's brand new science. As the world warms, a lot more forest will burn, possibly damaging stratospheric ozone. Could that extend the time of this La Nina dominance we're talking about as well?
Lots of things are possible. In that particular case, wildfire put a bunch of particles into the stratosphere which influenced the ozone hole, but the mechanism that it used requires the chlorine. So I think once the chlorine goes away, that mechanism may also weaken.
Good enough. At first I had a little resistance to your paper because I thought there was a conflict. In the back of my mind, I remember scientists not too long ago predicting there would be more El Nino events due to global warming. For example, there was a paper led by Bin Wang and PNAS October 21st, 2019, and it predicted more frequent extreme El Nino events. But then when I really sort of got past the press reading of it, he wasn't necessarily saying there would be more El Nino events. He was saying there would be more extreme ones. So maybe there isn't really a conflict there with your hypothesis.
Perhaps not, but there is an underlying problem here, or mystery, and that is that the vast majority of climate models show that the sea surface temperature would warm faster in the eastern Pacific than it does in the western Pacific, which is just the opposite of what we've been observing so far. So if the models are correct, then you might expect more intense El Niños because the eastern Pacific will already be warmer. But there's quite a bit of, I would say, controversy about whether the models are correct on that because of these other mechanisms that I've mentioned that might cause the East Pacific to actually cool as the climate warms up, which is what we've been observing. So there's a bit of a conflict between the recent observations that we've seen and what the climate models tend to do long term. Long term, they tend to give you an El Nino response in the equatorial Pacific, whereas what we've observed for the last 40 years is more of a La Nina response, a cooling in the eastern Pacific. So at present, we don't know if natural variability is doing this, if the ozone hole is doing this, if melting around Antarctica is causing the eastern Pacific to cool rather than warm. It's still a bit of a mystery, I think, and my paper is only one possible factor in a pretty complex story.
Your new paper in PNAS, and it is free to read, it's packed with climate knowledge. For example, how does the ozone hole affect Antarctic sea ice?
That's a good question. So strengthening of the winds, one would expect, would cause the surface waters to drift toward the higher latitudes. That would mean cooler water and ice would drift toward the equator, and you might think that that would cause the Antarctic sea ice to expand, but it's a little bit more of a complicated story than that because the winds in different locations around Antarctica and the undulations of the coastline of Antarctica have a big effect on what happens locally around Antarctica. But thinking about it in the most simple way, the enhanced westerly winds associated with the ozone hole would cause the surface waters to drift toward the lower latitudes, an effect of the rotation of the Earth. That would push cooler waters toward the lower latitudes. That would allow more the sea ice to expand. That would be the simplest physical theory for how the ozone hole would affect Antarctic sea ice. But it doesn't always happen that way because of the complications of geography and the east-west variations of the wind changes around Antarctica.
Well, we talked about whether there might be more El Nino events as the world warms, and this is really important for the world economy and governments and adaptation and all of that. But is it also possible that global warming itself will bring more La Nina years even after the ozone hole heals 50 years from now?
Yeah, I think it's possible because of there are mechanisms that could do that. As I mentioned, the deep ocean takes a lot longer to warm up, so you keep pulling up cold water essentially at a fixed temperature in the eastern Pacific while the rest of the world warms. There could be a long-term La Nina response due to global warming via that mechanism. That's not what the majority of climate models are doing. The majority of climate models are doing the opposite.
And as you mentioned, too, there could be other explanations for the increase in La Nina since 1980?
Yes. Well, the big one would be natural variability. There's something called the Pacific Decadal Oscillation or the Tropical Interdecadal Oscillation. That kind of looks like the El Nino-La Nina cycle, but it has a much longer time scale. And people have observed shifts in that over time. And there's a school of thought where the cooling in the Eastern Pacific that we've seen since 1980 is a form of natural variability not related to climate change at all.
Interesting. And you also helped, I don't know if you actually named it, but you certainly were right there at the ground floor of the Southern Annular Mode. I doubt our listeners know what that is. Could you give it to us in a nutshell?
Sure. So I mentioned that there's very strong winds at 60 degrees south climatologically in the Southern Ocean, but that the position of that jet moves north and south by about 5 degrees, and then we call it the Southern Annular Mode because it looks like a donut right around South America. The winds shift north and south. My work showed that that's a natural mode of variability due to the interaction of the storms in mid-latitudes and the westerly winds that they produce. Those westerly winds around Antarctica are there because waves in the atmosphere transport momentum poleward and create that jet. We call it an eddy-driven jet. And the eddies themselves grow on the jet. So if the jet moves to a different latitude, the eddies move to a different latitude, and they continue to sustain that jet in a different latitude. So it's very easy to move that jet around with some sort of small forcing like global warming or the ozone hole, because there's this natural mode of variability where the jet shifts north and south, and we call that the Southern Annular Mode.
And what happens there is big news for our Australian listeners in the kind of weather they're going to get.
Yes, it has a very strong influence in the Southern Hemisphere. Most of it's ocean, of course, but you do have New Zealand, Australia, and Chile and down there that are heavily influenced, as would be the Antarctic sea ice.
In a recent interview, Dr. Kevin Trenberth from the National Center for Atmospheric Research compared El Nino to a relief valve after several La Nina years, a kind of balancing mechanism. I sent your new paper to Kevin Trenberth, and after a quick read, he called it speculative but plausible. And that's pretty well what you say in your own conclusions. My take is you have the best answer yet to a very large mystery that needs to be solved. What do you say?
Yes, I think it is a bit speculative, but it's definitely physically plausible, and I certainly have found evidence for it in the observations, and also there's a large amount of theoretical and modeling and observational literature that would support this mechanism. So I think it's definitely a contributor.
As we wrap up here, what are you working on these days?
These days, I do a lot of work on tropical convective clouds and how they influence climate change. I also have done some work there where I have something called the fixed anvil temperature hypothesis. So an anvil cloud is that part that spreads out. It's an ice cloud that spreads out from a convection cell. You can see them in mid-latitudes associated with tornadic thunderstorms. They also appear in the tropics. So those high ice clouds cover a large fraction of significant fraction of the tropics, and they have interesting influences on the radiation balance. So we're trying to understand how those clouds will change as the climate warms up, and whether that will be a positive feedback, a negative feedback, or a completely neutral influence. So that particular problem is taking up most of my energy right now.
From the University of Washington, we have been speaking with Professor Dennis L. Hartman. His paper, The Arctic Ozone Hole and the Pattern Effect on Climate Sensitivity, is available in full text, a free read from PNAS, the Proceedings of the National Academy of Sciences. You can find links and more discussion in my show blog at ecoshock.org. Dennis, thank you for sharing your insights with our listeners.
My pleasure.
Science is great, but science is not enough. We also need to think about how we will deal with all this as a society and personally. In a coming show, we will talk with Carolyn Baker. She's a former psychotherapist and professor of psychology and history. Her latest book is Undaunted, Living Fiercely into Climate Meltdown in an Authoritarian World. Carolyn is putting out 2 free webinars you may want to attend. The title is What is this global crisis asking of us? The webinars are scheduled for 2 consecutive Thursdays later this September on the 15th and on the 22nd. Both start at 2 p.m. U.S. Eastern Daylight Time. Carolyn's co-host is Dr. Eric Garza, lecturer at the Rubenstein School for Environment and Natural Resources. You can send your ideas and tips to me at any time. The show email address is radio@ecoshock.org. I'm Alex Smith. Thank you for listening and caring about our world.
Radio EcoShock.